At nature's smallest layers, the rules you trust in daily life simply fall apart. Space stops dividing smoothly. Energy refuses to shift in gentle steps, and light won't act like a steady beam. Instead, experiments reveal that electrons leap. In fixed jumps, photons show up as single, indivisible units, and the core pieces of existence move in measured increments rather than flowing continuously. In this video, we examine the direct evidence that pushed researchers to discard traditional assumptions, from fixed energy jumps to strange wave-like behavior, from interference effects to sudden quantum changes. As we move through each section, we track how these findings combine to form a new vision of the universe, one where the smallest elements break every rule our senses expect to hold. With that direction in place, we open with the first question. Why does the quantum realm operate as though existence is composed of separate notes rather than one smooth stream? And the earliest place ordinary logic fails isn't near a cosmic boundary or inside a collapsing star. It shatters in something as simple as metal warmed by heat. At the dawn of the 20th century, researchers attempted to forecast how a heated material glows, how much radiation it releases at each shade as its temperature climbs. By classical thinking, energy should move seamlessly, light should appear in any amount, and nature should permit every possible value in between. Yet when scientists recorded the spectrum of this thermal emission with accurate tools, the results did not follow a smooth pattern at all. Regardless of how they changed their formulas, the figures refused to agree. Something had been overlooked. Max Planck, working in Germany in 1900, attempted a bold proposal to save theft from work. He suggested that energy was not continuous. Rather, it arrived in fixed units, tiny pieces that could not be divisible. He named these units quanta. With that single shift, the equations suddenly matched the observations. The curve of released light, which had stubbornly refused to align with classical expectations, fell neatly into order. Planck did not yet grasp what he had revealed in his private notes. He portrayed this concept as a nearly hesitant move, a numerical workaround to make the functions behave. But nature was sending him a message far deeper. At the tiniest levels, existence does not stream it. Clicks. A few years onward, Niels Bohr expanded it. Imagine trying to understand a song by only hearing a few isolated notes. That was science before we understood how atoms create light. Hydrogen, the simplest atom we know, shines in precise colors when heated, displaying crisp lines when its light passes through a prism. Researchers recorded those lines for decades, yet no one knew why only those particular hues appeared instead of an endless spectrum. The mystery lingered until a bold idea reframed the entire picture. Bohr argued that electrons don't drift freely inside hydrogen. They occupy fixed energy steps. They can't hover between values or settle wherever they please. When an electron drops from a higher step to a lower one, it releases a photon whose energy equals the gap between those steps. Since the steps are defined, the gaps are defined, and since energy determines color, the emitted light is fixed too. What once looked like random splashes of color suddenly became the mark of a rigid energy structure built into the atom. NASA later explained this idea with striking clarity. Quantum jumps happen exactly, never halfway. It isn't clever branding. It's supported by countless experiments. Electrons shift in precise amounts. They never release partial energy or land on imaginary steps. There is no smooth slide, only exact motion. Picture a ladder. You can stand on one rung or the next, but you can't float in the space between them. Electrons behave the same way. They occupy allowed positions and skip forbidden ones. Though simplified, this ladder analogy captures the essence of quantization. Atoms play from a fixed musical scale and cannot invent notes outside it. You see this every day without noticing. The yellow glow of sodium streetlights comes from electrons, dropping between specific levels that emit photons near a particular wavelength. Neon signs blaze red because neon atoms perform their own defined jumps. Firework colors, flame test streaks, and the spectral fingerprints of sunlight all arise from these quantized leaps. Atoms do not choose colors randomly. They're internal. Structure sets the palette. As technology advanced, scientists pushed the limits of this rule. Lasers with razor-thin frequencies and detectors tuned to. Microscopic shifts measured transitions inside atoms and ions with growing accuracy. The outcome stayed consistent. Quantum transitions obey strict boundaries. Even when pushed under extreme conditions, high magnetic fields, exotic plasmas, or isolated ions, in vacuum chambers the core pattern persisted. Electrons still moved in tidy, predictable jumps, rather than messy slides. These findings strengthened a deeper truth. Nature at its smallest scale behaves like a coded system, not a blurry continuum. That precision laid the foundation for innovations we now rely on. From lasers and atomic clocks to GPS and quantum computing, those jumps happened at precise values, repeatable to absurd accuracy. There was never a hint of anything in the middle. And that precision isn't confined to the part of the spectrum we can see. In deep space, hydrogen atoms quietly flip the alignment between an electron's spin and the proton's spin, releasing a radio signal at roughly 1420 megahertz, about 21 centimeters in wavelength. That single line is one of the most powerful tools astronomers use to chart the Milky Way's structure. Once again, the number is fixed. It comes from the energy gap between two quantum configurations, and that gap cannot be tuned or negotiated. Inside solid matter, electrons don't roam freely. They live within distinct energy bands. The separation between those bands, called the band gap, decides whether a substance acts like a metal, an insulator, or the finely balanced middle ground we call a semiconductor. Engineers craft LEDs, smartphones, and laser components by tailoring those gaps so electrons falling across them release light at chosen wavelengths. Your screen, your laptop, and the data pulsing through fiber networks all function because of energy levels deliberately engineered inside crystal lattice. Quantization isn't some quirky theory in dusty textbooks. It powers modern civilization. Beneath all this lies a deeper mathematical framework. In quantum physics, the permissible energies arise from solving the Schrödinger equation for bound systems, like electrons held near a nucleus. Only certain waveforms satisfy the physical constraints. These standing waves represent distinct energies. Think of a guitar string. It can vibrate only at particular tones when anchored at both ends. The length and tension allow only specific standing patterns. You can pluck it however you want, but the notes that endure are dictated by the instrument itself, inside an atom. The string isn't a literal strand of matter, it's the electron's wave function. Think of it as a mathematical rhythm. That tells us where the electron is likely to be found. Only certain wave patterns actually fit the atom structure, and each pattern carries a specific energy. That's why energy levels aren't random there. The natural resonant frequencies of the atom itself, as scientists probed even smaller scales, they hit a theoretical frontier, the Planck scale, named after Max Planck. This is where our familiar laws of physics may stop making sense. The Planck length about 1.6 times 10 cubed A meters, so small that space may no longer behave like a smooth fabric. Some theories suggest space-time might be built from tiny, indivisible units, like pixels of reality, and the same idea may apply to time. We treat time as continuous, but some models hypothesize, as small as possible, tick around the Planck time, roughly 5.4 times 10d seconds. Not proven, but the question remains, why does nature favor fixed steps instead of a perfectly smooth flow? History shows this pattern repeatedly. Quantized energy levels gave birth to quantum electrodynamics, the theory uniting light and matter with astonishing precision. Those same discrete levels keep atoms stable. Without them, electrons would collapse into nuclei and matter wouldn't exist. Because atoms absorb and emit light in sharp, repeatable energies, astronomers can identify elements in stars and galaxies through spectral fingerprints. Atomic clocks use the same principle, locking time to precise quantum transitions, accurate to the point of losing less than a second over the age of the universe. From street lights to satellites, chemistry to cosmology, one theme repeats: nature operates in steps. At human scale, those steps blur into smooth motion like heating water, where countless quantum events blend into a continuous temperature rise. But zoom in and the discreteness returns. Electrons jump. Photons carry exact energy packets. Every interaction is quantized. Reality has two faces, smooth on the surface, structured underneath. In this phase of our exploration, we've focused on the measured, verified side of that structure: spectral lines, energy ladders, instruments that prove them. But a deeper pattern is emerging. Wherever discreteness appears, waves and resonance follow like a shadow. And that leads us to a bigger question. Why do vibrating patterns recreate the rules of quantum mechanics, from energy levels to particle properties? What if matter isn't made of stuff at all, but of music waiting to be played? In the early days of quantum physics, long before headlines and documentaries, researchers began noticing something unsettling. Electrons leaping between energy levels weren't behaving randomly. They moved with the same kind of precision you see in a string vibrating in fixed patterns. A stretched string can only hold certain standing waves, only certain notes, number, tones in between. And that rhythm mirrored the exact jumps happening inside atoms. The deeper scientists pushed, the sharper that resemblance became. It wasn't poetic coincidence, it hinted at something fundamental. Carl Sagan once said, "We are made of star stuff, arranged by patterns we are only beginning to hear." What he didn't know was how literal that might turn out to be. Over time, physicists began to suspect that the pattern's shape in reality might be actual vibrations, tiny oscillations giving rise to particles, forces, and the supposedly solid world around us. So let's step deeper into that idea, where it began and why it refuses to disappear from physics. Our story starts decades before string theory ever existed. In the 1920s, scientists studied the wave-like nature of electrons. A young French physicist, Louis de Broglie, proposed a radical concept. Every particle carries a wavelength, not metaphorically, but physically. Electrons weren't tiny marbles orbiting the nucleus. They were waves traveling along curved paths, but waves looping in circles must obey a strict rule. Only certain wavelengths fit cleanly around the orbit. If the wave doesn't match the path, it cancels itself out. If it fits perfectly, it forms a stable pattern, like a musical note that resonates instead of fading. And from that simple insight, the first whispers of a universe built on vibration began to take shape. Suddenly, Bohr's quantized energy levels in hydrogen weren't just numbers on a chart, they made sense. They weren't random. They were the standing waves of the electron's internal vibration. It was one of the first real hints that the universe behaves like a resonant system, one where only certain patterns survive, while everything else fades. Away, just like the harmonics on a violin string. These patterns appear only at specific intervals. Shorter wavelength, higher energy, longer wavelength, lower energy. No mysticism required, just physics. And the evidence piled up fast. Hydrogen spectra, electron diffraction. Every experiment pointed toward the same uncomfortable conclusion. Particles behave like waves. But that raised a deeper question. If electrons act like waves, what exactly is vibrating? The answer didn't come from a laboratory. It came from theorists trying to unify the forces of nature. In the 1960s, high-energy experiments began uncovering a zoo of new particles, mesons, baryons, resonances that flashed into existence and disappeared in a heartbeat. The data looked chaotic until someone noticed a pattern. The masses of these particles lined up like musical harmonics, as if each particle was just a higher note of the same underlying vibration. That suggested something radical. These particles weren't fundamental objects. They were excitations of something deeper. Physicist Yuichiro Nambu proposed that these resonances behaved like stretched strings under tension. Low-energy vibrations produced light particles. Higher energy vibrations produced heavy ones. Those clues eventually evolved into what we now call string theory, the idea that the universe is built from unimaginably tiny strings of energy, each vibrating in its own mode. In this picture, an electron isn't a little sphere, it's a string vibrating one way. A photon is the same string vibrating differently. A quark is yet another pattern. The overwhelming diversity of particles suddenly looked like a musical scale instead of chaos. Strings could explain why particles come in families, why energy levels are quantized, why forces behave the way they do. It wasn't just elegant, it matched quantum math with unsettling precision. Picture a string fixed at both ends. It vibrates in its simplest mode, then in 2 segments, then 3, then 4. Each pattern is a different note, just like each vibration could be a different particle. Each vibration has its own frequency. Each frequency has its own energy. And in string theory, every allowed vibration corresponds to a specific particle mass, charge, spin. These aren't mysterious labels. They're just the fingerprints of how that string is vibrating. In this view, the universe isn't a bucket of separate building blocks. It's a catalogue of resonant patterns harmonics of a cosmic instrument. NASA puts it simply, particles exist only as quantized excitations, no vibration, no particle. Start the vibration, the particle appears. That's why particles pop in and out of existence during collisions, why one species transforms into another, and why quantum behavior feels less like chaos and more like choreography. Even Einstein's equations hint at this, when pushed to extreme precision. General relativity describes space-time like a deformable surface one that can ripple like a membrane. That's one reason string theory so naturally includes gravity, something other quantum models still struggle to capture. Then came a seismic shift in the 1980s. Physicists realized string theory doesn't work in just 3 dimensions. It needs extra spatial dimensions, tiny, hidden, curled up on lengths as small as 10 meters. These added dimensions weren't decoration. They were required for the math to behave. Think of a violin. The sound of a string depends on tension, length, and the shape of the wood around it. Change the body of the instrument, and the same string sings a different note. String theory works the same way. The geometry of those compact dimensions determines which vibrations are allowed. Change the geometry, change the particle spectrum. That's why theorists studied different ways extra dimensions might fold. Each configuration produces a different universe with different particles. Matter becomes a question of shape, and that geometric influence isn't just abstract. Math, it's a hint that the laws of physics might arise from the architecture of space itself. Data from NASA's Fermi Gamma Ray Space telescope has already placed strict limits on how the universe behaves. Specifically, limits on violations of Lorentz invariance, the principle that physics should look the same no matter how fast you move. These constraints quietly narrow the kinds of extra dimensions that could exist. The Planck spacecraft sharpened the picture even further, mapping the cosmic microwave background with stunning precision. It found no deviations from quantum field theory tightening, the allowed vibration patterns that could have existed in the early universe. And even the James Webb Space Telescope plays a role. By observing galaxies formed just moments after the Big Bang, its data pressures high energy physics models. The earliest light carries signatures of how particles behaved under extreme conditions. With each new measurement, the map of possible vibrations shrinks, leaving only those patterns consistent with reality. Still, string theory remains unproven, powerful, compelling, but unfinished. Why discrete energy levels? Why families of particles? Why quantization at all? Again and again, the answer circles back to vibration. While physics often advances by adding new pieces, new particles, new forces, new equations, string theory does the opposite. It simplifies. It suggests that under the apparent chaos of the quantum world lies a single unifying idea, resonance. And this theme stretches across history. Johannes Kepler looked at planetary orbits and turned them into musical intervals, believing nature followed harmony. Maxwell unified electricity and magnetism and discovered not static structures, but waves. Quantum mechanics reintroduced standing waves at the atomic scale. Across centuries, vibration keeps returning as the hidden language of nature. And even though string theory is incomplete, the pattern is impossible to ignore whenever physics digs deeper. Something is vibrating. But that leads us somewhere stranger somewhere, more personal, if what we call particles are just vibrations. Then how does a vibration become a localized dot on a detector? How does something wave-like become something solid? Part 3 begins here. Particles don't exist as tiny permanent objects. They appear only when waves are grieved and many overlapping. Vibrations align for a moment, then fade back into possibility. This idea overturns centuries of intuition. It suggests that matter is not a thing, but a temporary event. Werner Heisenberg hinted at this when he wrote, "What we observe is not nature itself, but nature exposed to our method of questioning." To understand why particles appear, we return to the experiments of the 1920s. Electrons, once imagined as miniature spheres, behaved like waves. Fired at a metal surface, they produced interference patterns, rippling like water in a pond. They interfered with themselves, but when observed, they did not smear across the detector like a wave. They struck a single point, sharp and sudden like a particle. This contradiction haunted early quantum theory. The resolution arrived slowly. Electrons are neither objects nor waves by themselves. They are wave packets, brief convergences of many waves interfering just right to produce a localized peak of probability. Picture waves with slightly different wavelengths. When added, sometimes their peaks overlap and amplify, forming a strong pulse. Other times they cancel out. That fleeting pulse when many waves resonate in unison is what we interpret as a particle. When the alignment decays, the particle spreads. When the alignment returns, the particle reappears. This duality is not a contradiction. It is the signature of waves constructing temporary, localized forms. In physics, this process has a name: Fourier synthesis. A particle doesn't emerge from a single wave, it's born from many waves overlapping just long enough to form a temporary bundle of energy. It exists only as long as those waves stay in sync. And this leads to a shockingly simple explanation of the uncertainty principle. No equations required where multiple waves overlap tightly in space. They create a sharp, localized pulse. That pulse is what we recognize as a particle appearing at a specific point. But squeezing waves together requires mixing many different wavelengths. Different wavelengths mean different momenta. So even though the position is precise, the momentum becomes uncertain. Try to make the momentum precise, and you have to use waves with almost identical wavelengths. But identical wavelengths can't form a tight packet. The particle spreads out. Position becomes uncertain. Uncertainty isn't a philosophical mystery, it's a consequence of how waves stack. Particles appear when waves line up. They disappear when they drift apart. This wasn't hypothetical. In 1958, Claus Janssen ran interference experiments that demonstrated the wave behavior of electrons with stunning clarity. Then in 2002, researchers in Vienna repeated the effect. Using massive organic molecules, over 100 atoms, and still saw interference patterns. Even complex matter behaves like waves. Quantum wave packets aren't just a microscopic curiosities, they show up everywhere. NASA's Jet Propulsion Laboratory uses wave packet models to understand how cosmic rays disrupt spacecraft electronics. The Gaia mission, mapping over 1 billion stars, requires ultra-precise wave models of photons. Even tiny errors could distort measurements across thousands of light years. and the James Webb Space Telescope relies on quantum interference models to detect light so faint it sometimes arrives just a few photons at a time. Every modern instrument that measures light depends on this understanding. Every observation of the universe echoes it, but the clearest window into wave packets came from time-resolved electron microscopy in the late 2000s. Scientists fired ultra-fast bursts of electrons at AG materials while synchronized lasers recorded how their wave packets evolved in real time. They didn't just calculate quantum behavior, they filmed it. Electrons weren't sitting still like tiny marbles. They spread, interfered, collapsed into localized peaks, and dispersed, again shifting between wave and particle depending on how tightly their components lined up. Matter stopped looking like a thing and started looking like a recurring event pattern that must constantly rebuild itself to exist. To see how waves form something localized, physicists often turn to music. A single pure tone spreads smoothly, filling space evenly. It can't pinpoint a location, but a sharp pluck contains many frequencies at once, creating a compact burst that exists in a defined moment. The wave is the background. The particle is the pluck the moment many harmonics cooperate. This idea forms the backbone of modern quantum mechanics. It powers high-energy simulations, electron imaging, and particle accelerator design. At CERN, wave packet models predict where particles will appear after collisions at nearly light speed. Those predictions worked. They played a central role in identifying the Higgs boson in 2012. If particles were solid, none of this would work. But because they're interference patterns, temporary bundles of waves, physicists can calculate where they'll materialize, and those predictions match reality. As we follow this path further, a subtle shift comes into focus. A particle only exists from moment to moment because deeper waves line up just long enough to create it. Change those waves slightly and the particle's traits shift. Change them too much and the particle simply vanishes. Matter isn't the foundation. The waves are. The particle is the footprint they leave when they cooperate long enough to be. Notice seen this way, many disconnected ideas in quantum mechanics suddenly snap together. Uncertainty becomes a natural outcome of wave interference. Wave-particle duality stops looking like a contradiction and instead becomes two perspectives on the same underlying structure. Waves converging create something local. Waves drifting apart erase it. Measurement is simply the act of holding one of those convergences in place long enough to record it. That's why Heisenberg's words still sting. We don't observe nature itself, we observe what our way of questioning forces into visibility. We don't see the full wave field. We see the tiny moment when it nods into a particle our instruments can catch. Just as that realization settles in, something stranger steps forward. A beam of light is sent toward to open paths. The underlying wave spreads through both slits, forming an interference pattern that requires multiple routes. Yet when we measure the result, the energy shows up as one localized hit, a single, indivisible particle. This pushes us into the next question. Why does light behave like a wave when traveling, but land like a single particle when observed? This is the most unsettling fact in physics. A single photon can take multiple paths at once, yet it always arrives as a single point of energy. No classical logic survives that transition. Richard Feynman put it bluntly, nobody truly understands quantum mechanics. To see why, we return to the experiment that forced those words into existence. The double-slit experiment. It began in the early 1800s, long before anyone imagined photons. Thomas Young cut two narrow slits into a thin card and let light pass through. If light were made of tiny pellets, two bright stripes would appear. If light were waves, they'd overlap and form a pattern of bright and dark bands. He saw interference. Light behaved like a wave, but a century later, physicists discovered light also came in indivisible packets photons. So the experiment was repeated using light so faint that photons passed one at a time, separated by long pauses, unable to interact with each other. Yet the interference pattern still appeared. By ... each photon landed at a single location, like a particle, but the pattern only emerged when both slits were open, like a wave. One photon somehow behaved as if it traveled through both paths. This wasn't speculation, it was replicated endlessly. Light wasn't choosing a route, it was exploring every possible route. To explain this, physicists turned to the wave functioner, mathematical structure describing every path a particle might take. As the photon approaches the barrier, the wave spreads and touches both openings. Each slit produces a fresh wave front, and the two fronts overlap. Aligned waves reinforce, misaligned ones erase. The interference pattern appears from possibilities, but the particle-like detection emerges only when the wave interacts with the screen. At that instant, all those possibilities collapse into one location. That collapse isn't a physical burst, it's a shift in information, a narrowing of potential into a single event. Modern space telescopes rely on this behavior. Missions like JWST require precise models of how single photons evolve as waves and collapse upon detection. Without that understanding, faint cosmic, light couldn't be measured at all. The math is intricate. The idea is simple. Light moves like a wave. It lands like a particle. Not because it switches identities, but because both behaviors are shadows of a single underlying structure. The turning point came when physicists finally asked what happens if we compel a photon to reveal which slit it actually passes through. During the 1970s and 1980s, researchers placed extremely sensitive detectors near the slit's devices, capable of identifying a photon's path without blocking it. The results were astonishing. Whenever a path detector was activated, even with minimal disturbance, the interference pattern disappeared. Each photon behaved like a particle, selecting one slit or the other. But when the detector was turned off, the interference pattern returned. On, pattern gone. Off, pattern restored. Unobes, ERVED. The photon does not travel through a single slit, behaves as a wave exploring multiple paths simultaneously. Once we obtain path information, the wave collapses early, forcing the photon to behave like a localized particle. Richard Feynman once remarked that the double-slit experiment contains the only real mystery of quantum mechanics, because measurement does more than reveal information, it changes the outcome. But this change isn't supernatural. It is the natural behavior of wave functions. They extend outward until interaction forces them to localize. A clearer picture emerged in the 1990s through experiments using single photon interferometers. Scientists employed beam splitters and mirrors to divide a photon's wave function into multiple paths of different lengths. By adjusting those lengths by fractions of a wavelength, they could shift the interference pattern predictably. This demonstrated that a photon's behavior depends on the structure of the entire path network, not just any single segment. Modern technology confirms this principle. Quantum communication satellites depend on precise path length calibration. Tiny alignment errors shift interference patterns across thousands of kilometers. ESA's quantum teleportation experiments over distances beyond 1,000 kilometers rely on the same interference effects. Even the detectors on the James Webb Space Telescope must model internal quantum interference to convert incoming photons into electrical signals. All of these systems rely on the same principle revealed by the double-slit experiment. Photons travel as waves, exploring multiple possibilities, but detection collapses that wave into a single localized event. To understand why the photon arrives at a single point despite traveling as a wave, consider a simple analogy. Drop pebbles into water at different times and watch the ripples overlap. The interference pattern shows where waves amplify or cancel. It does not tell you where a pebble lands. In quantum physics, the wave defines the probability landscape, while the particle is the final event of detection. The photon appears at a single location because detection is a localized energy transfer. The wave predicts where it might arrive. The particle is where it does arrive. There is no contradiction once we separate motion from measurement. During travel, wave. At arrival, particle. One variant of the double-slit experiment deepens the mystery. The Delachoise experiment proposed by John Wheeler. In this version, researchers decide whether to measure which path a photon took after it has already passed the slits. The outcome still matches the later choice. This doesn't mean the photon knew the future. It means the wave function does not collapse until measurement. Its history is not fixed until interaction completes. This isn't time travel. It's simply how wave functions behave. And while this challenges intuition, every quantum device we use operates according to this principle. We have now traced the photon's journey, a spread-out wave exploring many paths, followed by a sudden, localized arrival. We've seen how observing the path destroys interference, and how allowing the wave to evolve preserves quantum behavior. But the next step goes beyond single photons. When two particles are prepared together and then separated by meters, kilometers, or even across a galaxy, their measured properties remain correlated in a way classical physics cannot explain. No signal travels through space. No force connects them. Yet a change measured in one is reflected instantly in the other, regardless of distance. Einstein called this spooky action at a distance, insisting no correct theory should permit such behavior. But every experiment ever conducted confirms it. The story begins in 1935 with a paper by Einstein, Boris Podolsky, and Nathan Rosen describing what is now called the EPR paradox. They imagined two particles created together and sent in opposite directions. Their properties, having interacted, become linked and tangled in a way classical physics cannot separate. Einstein argued that measuring one particle should not instantly determine the other's state unless hidden information traveled with them. He called this principle local realism, the belief that objects have definite properties independent of measurement, and can influence only their immediate surroundings. Quantum theory disagreed. It described the pair as a single shared wave function, spanning both particles. Measuring one forces the entire system to settle into a definite configuration. Einstein rejected this idea, insisting the true state must exist before measurement. Quantum mechanics said the opposite. The debate remained theoretical until 1964, when John Bell derived what became the Bell inequality mathematical condition any local, realistic theory must satisfy. Quantum mechanics predicted it would be violated. This transformed the argument into an experimental test. In the 1980s, Ayling-Aspect performed the first major test. Entangled photons violated the Bell inequality. Local realism failed. Quantum mechanics was correct. More precise experiments followed. For decades, Delft University closed the locality loophole using entangled electron spins separated by over a kilometer. NIST achieved real-time random switching of measurement settings. In 2015, multiple teams published loophole-free Bell tests. By 2018, China's Messier satellite performed tests over 1,200 kilometers. The inequality was violated again. Distance did not weaken the correlation. To understand why this behavior feels so strange, we must step back. Entangled particles are not two separate entities with separate wave functions. They are one system described by one wave function extending across space. Measuring one does not send a signal to the other. It collapses the shared structure. A helpful analogy is a stretched string held at both ends. Plucking one end doesn't send a message to the other. It simply excites the string's overall state. Entanglement works the same way. The particles are not connected through space. They are connected through structure. This is why distance does not matter. The wave function does not reside in physical space. It exists on a mathematical structure that overlays space. That structure can correlate outcomes instantly because it is not limited by the speed of light. The speed of light restricts signals traveling through space, but entanglement operates within the deeper framework that defines what space is in the first place. NASA and ESA rely on this understanding in the design of quantum communication systems. The Messier satellite demonstrated long-distance entanglement transmission through the upper atmosphere, showing that interference patterns remain intact even after photons pass through over 100 kilometers of turbulent air layers. This provides direct evidence that entanglement can maintain coherence under extreme environmental conditions. Similarly, ESA's quantum teleportation experiments in the Canary Islands transmitted entangled photon states across more than 140 km. Despite atmospheric scattering and shifting weather patterns, the entanglement remains stable. These systems demonstrate that entanglement is not fragile or mystical. It is a measurable physical phenomenon robust enough to drive real technology. To visualize entanglement without equations, consider this. When two entangled particles are measured, their combined results display correlations stronger than anything classical probability can produce. No matter how cleverly designed, two classical dice will never yield correlations beyond classical limits. Entangled particles do, and they do so consistently. This is why Bell's inequality matters. It shows that entanglement cannot be explained by hidden instructions carried from the past. The correlations are not predetermined. They arise at the moment of measurement, governed by the structure of the shared wave function rather than the physical distance between particles. The implications are philosophical, but the data remain clear. Distance does not weaken entanglement. Time delays do not diminish it. Space does not constrain it. This leads to a quiet realization. The space we imagine stretching between objects may not be fundamental. It may be a derived surface emerging from deeper connections. Modern research in quantum gravity points in this direction. Some models propose that space-time geometry arises from networks of quantum entanglement. That space is the fabric stitched together by these quantum relationships. Whether these models survive future testing or not, they share a central idea. Entanglement is not a property of space. Space may be a property of entanglement. And just as we begin to accept that distance no longer holds its traditional meaning, a subtler realization emerges. If entanglement weakens the importance of space, then time, the order in which events unfold, begins to show cracks as well. The next phenomenon does not arrive with shock, but with a quiet suggestion. The future may influence the past in measurable ways. Part 6. Why the universe behaves as though time does not move in one direction, but responds to future conditions. The most startling shift in quantum physics is not that particles behave like waves, nor that distant partners seem to ignore space. It is that photons sometimes appear to behave as though future measurements shape past behavior. This is not metaphor. It is experiment. It is data. And it challenges the idea that time marches forward in a single direction. John Wheeler described this unsettling idea in a sentence that still guides quantum research. No phenomena is a real phenomena until it is an observed phenomena. This principle takes form in a family of tests known as delayed choice experiments, which show that decisions made after a photon has already passed a critical point can determine what the photon must have done. Earlier, not by altering history, but by revealing that the past remains undefined until measurement locks it into place. The origin of this idea reaches back to the 1970s, when Wheeler asked a simple but profound question. If light behaves as a wave while traveling and as a particle, when detected, then when does it decide which role to play? Does the choice occur at the moment the photon encounters a fork in its path, or only later, at the detector? To investigate, Wheeler proposed a variation of the double-slit experiment in which the decision to reveal or erase the photon's path is made after the photon has already passed the slits. If photons behaved like classical objects, the result should not depend on what happens later. A photon that traveled through one slit would eliminate interference. A photon that traveled as a wave through both would create it. But Wheeler predicted something stranger. The interference pattern would depend on the later choice. The future measurement would determine the earlier behavior. The first experimental tests began in 1978. By 2007, precise implementations of Wheeler's design were carried out using single photons in interferometers at the University of Queensland. The result was unmistakable. The photon's earlier behavior depended on the final measurement. It did not commit to a path earlier. The past was not fixed until the end of the measurement chain. To see how this was confirmed, imagine a simple interferometer. A photon enters. A beam splitter divides its wave function into two paths. Mirrors redirect the paths. Then, just before they recombine, experimenters choose whether to insert a second beam splitter. Insert it, and the two paths interfere like a wave. Remove it, and the photon appears to have taken one definite path. The key is that this decision is made after the photon has already passed the first beam splitter where the choice should have occurred. Yet the photon behaves consistently with the later decision. Insert the beam splitter, and interference appears. Remove it, and the interference disappears. The past remains open until the present decides. This remains consistent across modern technologies. NASA, ESA, and quantum optics laboratories use this principle in photon routing systems, where wave functions remain uncollapsed until detection, enabling interference control over hundreds of kilometers. A more dramatic version came in 2007 from Ailing Aspects Group in France. They used high-speed random number generators to decide whether to reveal or erase path information after the photon had already passed the slits. The random choices were made in less than a microsecond too quickly for any signal to travel between the location of the photon split and the location of the choice. Yet the photon's earlier behavior still depended on the later decision. This showed that the universe does not require backward-traveling information. Instead, it does not finalize a past event until measurement completes the process. The past is not rewritten. The past is not fully written until observation. This structure becomes clearer when we describe the photon using its wave function, a mathematical object that contains all possible histories. Before measurement, many histories remain viable. After measurement, one crystallizes. The photon does not have a single fixed past. Its past depends on the conditions of detection. This behavior appears across modern quantum systems. Cold-atom interferometers on the International Space Station keep atoms in superposed paths for meters at a time. Their earlier trajectories are not finalized until detection collapses their wave functions. Laser interferometry for gravitational wave detection relies on stable interference patterns produced by beams, whose earlier path properties remain unresolved until the moment they strike the sensor. Even JWST's infrared detectors register photons, whose histories only become definite at the instant of arrival. The universe waits to decide until interaction forces its hand. A famous extension of Wheeler's idea is the quantum eraser experiment, demonstrated in 1999 by Yoon-Ho Kim and colleagues. Photons are split into pairs. One goes through a double-slit system while the other travels elsewhere. By manipulating the partner photon even after the first has already struck the screen, researchers can create or erase interference patterns. This does not imply retroactive signals. It means that interference emerges only when the entire history, including the partner's measurement, is taken into account. The phenomenon reveals how deeply interconnected quantum processes are. A photon's behavior is determined by the full context of the experiment, not just by events that occur earlier in time. Its trajectory exists only within the complete experimental setup. Change any part of that setup, even one introduced later, and the inferred history changes with it. This forces physicists to reconsider how time is treated in quantum theory, not as a philosophical curiosity, but as a rigorously testable feature of the mathematical framework. Multiple models attempt to explain delayed choice behavior within standard quantum mechanics. They differ in interpretation but agree on observable predictions. One perspective treats the wave function as a collection of possible histories. Measurement reduces those possibilities to a single self-consistent chain, one that must satisfy global constraints, not merely local temporal order. Another interpretation, used in quantum information theory, models the wave function as information, evolving through a reversible computation. Past and future constraints must align to produce a valid outcome. In the path-integral approach inspired by Feynman, the photon explores all possible paths simultaneously with the final measurement, reinforcing some histories and cancelling others. Across all models, the central idea is consistent. Certain aspects of a system are not fixed until measurement, delayed choice. Experiments now extend far beyond laboratory optics. They appear in satellite communication research, quantum random number generation, and proposed space-based quantum networks. China's Messier satellite has already distributed entangled photons over distances exceeding 1,000 kilometers, and future missions plan to incorporate delay choice protocols to enhance security and detect interference. In these systems, photons travel long distances with their histories unresolved until final detection. This is not a theoretical novelty, it's a practical feature of contemporary technology at the boundary of these experiments. One implication becomes clear. Like space under entanglement, time appears less absolute than previously assumed. Its order may not be rigid. Events may not settle into a definite sequence until the full measurement context is defined. If space is a surface concealing deeper structure, time may be one of the threads woven through that structure, not a single directional arrow, but a web of allowable relationships. And as that idea settles, another consequence emerges, one rooted not in paradox, but in communication itself. Part 7. Why does quantum encryption offer perfect security, while revealing that reality responds fundamentally to observation? One of the most striking aspects of quantum physics is that observing a photon can alter it irreversibly. This change is so clear that even a subtle eavesdropper cannot avoid detection. This is not metaphor. It is the operating principle behind quantum communication technologies, as stated in quantum communication briefings. Observing a quantum system inevitably disturbs it. This principle forms the basis of quantum key distribution, QKDA, method of transmitting encryption keys through photons whose quantum states shift if intercepted. This is not security through mathematical difficulty, but through physical law. The idea traces back to the 1970s, when researchers realized that measuring a quantum system changes it. Classical measurement as passive view can look at a chair without reshaping it. At the quantum scale, measurement collapses the wave function, and that collapse cannot be undone. This fragility became the foundation of QKD. The first major implementation was the BB84 protocol, developed in 1984 by Charles Bennett and Gilles Brassard. In BB84, information is encoded in the polarization of photons, the direction their electric field oscillates. These photons are transmitted individually, and because they are quantum objects, they exist in superposition until measured. If the receiver measures a photon using the correct basis, they recover the encoded bit accurately. If they choose the wrong basis, the photon's state is disturbed and the result becomes random. And if an eavesdropper intercepts the photon, they must measure it to extract information, an action that irreversibly alters the photon's state and introduces detectable errors. The sender and receiver then compare a subset of their results publicly. If the error rate exceeds a known threshold, they can conclude that the transmission was compromised. The elegance lies in its simplicity. The laws of physics revealed the intrusion. Early real-world deployment began in the 1990s, when researchers transmitted quantum keys through urban optical fiber networks. Initial distances were short, only a few kilometers, But the principle held consistently in the early 2000s. Advances in detectors extended QKD to distances exceeding 100 kilometers. By 2017, China's MISIUS satellite distributed entangled photons across 1,200 kilometers of free space, linking ground stations separated by entire provinces. Each demonstration confirmed the same rule. Any attempt to observe a quantum key leaves a measurable trace. Later, collaborations between ESA and the Austrian Academy of Sciences transmitted entangled photons between La Palma and Tenerife, a span of over 140 kilometers through the atmosphere. The signal survived turbulence and scattering, but not measurement without disturbance. This is the foundation of quantum encryption. It is not secure because it is complex, but because undetected observation is physically impossible. To understand why observation is so disruptive, we look at how photons form quantum states. A photon's polarization may be horizontal, vertical, or a superposition of both analogous to a spinning coin that has not yet landed. When a receiver measures the photon, the state collapses and the outcome becomes definite. An eavesdropper forces that collapse prematurely, destroying the original superposition. Once elapsed, the prior state cannot be restored. Classical information behaves differently. If someone reads your email, the email remains intact. If someone reads your quantum key, the key is altered and the alteration itself becomes evidence of intrusion. Quantum encryption deepened with entanglement-based protocols such as Eckerd's E91 scheme. In these systems, entangled photon pairs are shared between the communicating parties. Measuring one photon determines the correlated state of its partner, regardless of distance. No interception can occur without destroying the entanglement, producing not just errors, but observable violations of Bell inequalities. If the inequality is violated, the key is compromised. If it holds, the channel remains secure. What once troubled Einstein becomes a practical tool for information security. Modern quantum communication expands these principles even further. The European Space Agency's Mosaic initiative aims to create a global satellite network for quantum key distribution. NASA's Deep Space Optical Communication programs investigate similar systems for interplanetary missions. These techniques rely on single photon transmission through space, with wave function collapse occurring precisely at detection. The same vulnerability that makes quantum states sensitive to interference also makes them ideal for secure communication. The act of observation becomes part of the message. In quantum systems, measurement is not passive, it is a physical interaction that changes the state of the system. This is not a technological limitation, but a feature of the underlying physics. Quantum randomness is not noise. It is structure. It protects information not through complexity, but through constraints on what can be known simultaneously. The Knock-Cloning theorem illustrates this directly. Unknown quantum states cannot be perfectly copied. If cloning were possible, an eavesdropper could duplicate a quantum key undetected. Instead, nature prohibits copying, preserving security by making information inherently fragile to probing. This protection arises from the structure of wave functions. Yet the principle can be stated simply. One cannot observe a quantum system without becoming part of the outcome. This principle forms the foundation of unbreakable quantum encryption. They determine what becomes real. ESA states it clearly. Any observation inevitably disturbs the quantum system. Hidden inside that disturbance is the beginning of something entirely new. Machines that use superposition not to conceal information, but to explore multiple possibilities at once. Machines that do not settle for a single state, but evaluate many simultaneously. The same physical laws that make quantum keys secure enable a new form of computation. Part 8. Why do quantum computers threaten classical encryption by exploiting the very superposition we struggle to interpret? The most disruptive shift in modern technology is not a new telescope or particle. Discovery it is the realization that devices built from delicate quantum states can solve certain problems in seconds that classical computers would need millennia to finish. This is not theoretical. It is demonstrated in systems cooled to near absolute zero and isolated from environmental noise so completely that even background radiation must be filtered out. Google's quantum computing team summarized the breakthrough in a single line. The task would take 10,000 years on a classical supercomputer, 1 second on a quantum processor. To understand why, we start with a core principle. A classical bit is always 0 or 1. A quantum bit, a qubit, can be 0, 1, or a superposition of both. When multiple qubits are entangled, the number of simultaneous states grows exponentially. A system with just 300 qubits represents more possible configurations than there are atoms in the observable universe. No classical architecture can simulate that state space directly. The idea emerged in the 1960s when Richard Feynman recognized that classical computers were fundamentally inefficient at simulating quantum systems. His proposal was radical, too. Model quantum physics. You would need a computer that itself obeyed quantum laws. The concept remained theoretical until laboratories learned to control individual photons, trapped ions, and superconducting circuits. Major progress arrived in the 2000s as teams at IBM, MIT, Google, and the University of Innsbruck built multi-qubit systems, stable enough to run real algorithms. The engineering challenge is immense. Quantum states collapse when disturbed. Qubits often operate near 0.015 Kelvin, colder than deep space. They must be shielded from stray photons, mechanical vibrations, cosmic rays, and radio signals from distant cities. Yet despite these constraints, functioning quantum processors emerged and their performance surprised even their designers. To understand the advantage, imagine a classical computer attempting to crack a lock with 1 billion combinations. It must check one at a time. A quantum computer places the lock into a state where all combinations exist simultaneously. It does not test possibilities sequentially. It encodes them in parallel, but it cannot simply read out every answer. Measurement destroys superposition. Instead, quantum algorithms reshape the wave function so that incorrect possibilities cancel out while correct solutions reinforce each other. Superposition generates the possibilities, interference filters them, measurement extracts the result. Quantum computation is not brute force. It is optimization over probability landscapes. A defining example is Shor's algorithm, 1994, which showed that quantum computers can factor large numbers exponentially faster than classical machines. This matters deeply because global encryption, systems from banking to secure messaging to military communications, depend on the hardness of factoring. Classical computers cannot do it efficiently. Quantum computers can. When Shor proposed his algorithm, no hardware existed in which to run it. By 2019, Google's Sycamore processor demonstrated the raw performance needed to make such attacks plausible. Research groups worldwide are now racing to build systems with sufficient qubit counts, stability, and error correction to run cryptographic-grade workloads. This threat is no longer theoretical. Governments and research labs are already developing post-quantum algorithms, mathematical replacements designed to resist quantum-based attacks. NASA, ESA, and cybersecurity agencies closely monitor these developments. Even though quantum computers are still emerging, the direction is clear. Any lock protected by classical computational difficulty is becoming obsolete. How these machines physically operate is just as fascinating. Different laboratories use different approaches, each with unique advantages and challenges. Here are three major platforms, explained simply. Without Equasus.1, superconducting qubits used by Google, IBM, and many national labs. These are tiny loops of superconducting material, cooled close to absolute zero. Each qubit corresponds to a specific current pattern within the loop. Microwave pulses control and measure superpositions. They operate quickly, but they are highly sensitive to noise. 2 Traption qubits used by the University of Innsbruck, Honeywell, and IonQ. Individual atoms float inside electromagnetic traps, and lasers manipulate their internal energy levels. These systems are extremely stable and precise. 3 Photonic qubits used by the University of Bristol, Xanadu, and space-based quantum communication platforms. Information is encoded in photons and can be transmitted through optical fibers or even space. NASA's deep space optical communication experiments explore photonic systems for secure transmissions across millions of kilometers. The Mosaic program works toward quantum satellite networks using similar principles. Every photon sent between ground and orbit must preserve superposition long enough to carry information securely. Each system shows a universe where superposition is not just a theoretical curiosity, is a tool, a resource, something usable. The most dramatic demonstration of quantum computation came in 2019, when Google announced quantum supremacy. The moment a quantum processor performs a task no classical computer can feasibly achieve. Their processor solved a random circuit sampling problem in about 200 seconds. Google estimated that the world's most powerful classical supercomputer would take 10,000 years to complete the same task. Whether that number shifts with improved classical algorithms, the scale of the advantage is undeniable. The claim that shook the world was simple. What takes 10,000 years on a classical computer takes roughly 1 second on a quantum processor. This accomplishment didn't break encryption, but it confirmed the quantum architecture can deliver exponential acceleration. If scaled, it wouldn't simply challenge old cryptographic systems, it would redefine what computation means. But quantum computers don't just threaten locks, they open doors. Scientists use them to simulate molecules that classical computers cannot handle. Modeling molecular vibrations, reaction rates, and binding properties could transform medicine, energy, and materials science. These simulations require handling wave functions with thousands of interacting components at tasks classical systems cannot perform. Quantum simulators built at MIT and Harvard have already demonstrated control over hundreds of entangled atoms. These experiments reveal how magnetism, superconductivity, and exotic phases of matter emerge from collective behavior. NASA is studying quantum algorithms that could optimize interplanetary trajectories, reducing computation time from months 2 minutes, and is investing in quantum-based sensors capable of detecting gravitational anomalies with unprecedented precision. All of these breakthroughs rely on the same fragile resource: superposition, the condition of existing in many possibilities at once. But this fragility reveals something deeper. To build a quantum computer, researchers must protect superposition from every disturbance: thermal noise, cosmic rays, stray photons, vibrations. Any interaction can collapse the quantum state prematurely. This exposes a truth that echoes throughout quantum physics. The universe responds to observation, and quantum systems evolve differently when left untouched. This is not philosophy. It is the practical lesson learned in every quantum laboratory, every experiment, every qubit that decays under the wrong measurement. The heart of quantum computing is the heart of measurement theory itself. Information is physical, and extracting it changes the system as quantum processors scale from 128 qubits to 433 qubits to 1,000 qubit prototypes. New mysteries emerge, not only about physics, but about ourselves. For the first time, we have machines that operate in realms we cannot intuitively visualize. Machines that compute using rules our senses cannot access. Machines whose power comes from embracing states that exist only in the mathematics of wave functions and the silence of cryogenic chambers. This forces new questions. What does it mean to build something that thinks in probabilities? What does it mean to trust a machine that derives truth from superposition? Where do we fit in a world where computation expands beyond classical limits? From here, the next step becomes clear. Part 9. Why does consciousness seem to echo? Quantum behavior, from hidden processing to mysterious thresholds. The most striking shock in this journey isn't found in particles, photons, or entanglement. It is the realization that the human brain sometimes behaves with boundaries and jumps that resemble quantum transitions, not because neurons are small or mystical, but because the mind reveals discontinuities, hidden layers, and non-linear thresholds that mirror the abrupt switches observed in quantum systems. Roger Penrose captured this tension in a single sentence that still challenges neuroscience. Consciousness must involve non-computable ingredients. We now step into the data behind these claims, not speculation, not metaphysics, but documented cases where awareness appears in discrete steps, vanishing and emerging the way quantum events do, as if the brain has its own versions of wave packets, thresholds, and collapses. The first clue comes from blindsight. In the 1970s, neurologist Lawrence Weisgrant studied patients whose primary visual cortex had been damaged. They reported total blindness in parts of their visual fields, yet under controlled tests, they could correctly identify motion, locations of flashes, and even facial expressions they insisted they could not see. They lacked conscious vision, yet some layer beneath awareness still processed the signal. The transition between no awareness and awareness was not gradual. There was no fuzzy middle zone. It behaved like a threshold. Below it, nothing enters. Consciousness, above it, the signal suddenly appears. The brain flipped between discrete states not because neurons are quantum particles, but because the mechanism of awareness respects sharp boundaries similar to quantized energy levels. A second clue comes from micro-awareness, discovered in studies of near-threshold stimuli using high-speed EEG and fMRI. Researchers found that very weak signals sometimes trigger brief flickers of awareness lasting under 50 milliseconds. These moments follow rules reminiscent of wave interference. Multiple weak signals can combine and reinforce each other until they cross the threshold into conscious perception. When signals align, awareness appears. When they fail to align, the signal remains unconscious. This dynamic interplay reinforcement, cancellation, threshold crossing, parallels the behavior of wave packets. The structure is wave-like, and the transition is abrupt, not gradual. Just as electrons jump between states without intermediate positions, awareness jumps from unconscious to conscious once enough reinforcement accumulates. This is why Penrose argued classical computation might be insufficient. The transitions look non-linear, not continuous. Another clue comes from neural ignition, observed in the late 2000s using depth electrodes implanted in epilepsy patients. Scientists recorded the timing and structure of neural firing during moments of conscious perception and discovered that awareness does not emerge gradually. Rather, it appears when a specific pattern of firing crosses a boundary all-or-nothing switch. Below the threshold, neurons fire independently, processing fragments of information. Above it, a sudden burst of synchronized firing spreads across the cortex. It resembles a phase transition like liquid water snapping into ice at a critical temperature. This is the same mathematical structure behind quantum phase transitions at absolute zero. Again, this does not mean the brain is quantum, but the shape of the transition is quantum-like, non-linear, abrupt, respecting discrete boundaries. These findings parallel the claims of integrated information theory, II. II suggests consciousness corresponds to integrated, not isolated, information. Awareness emerges when distributed processes bind into a unified whole, much like entanglement, links distant quantum particles into a unified state. The transitions are sudden. Signals either become part of the network or remain invisible to awareness. There is no half-conscious in between. Measurements from intracranial electrodes show these transitions occur in tens of milliseconds. Before ignition, information is fragmented. After ignition, it becomes globally accessible. This dynamic resembles the collapse of a wave function. Before collapse, many possibilities. After collapse, a single coherent outcome. The analogy is not physical, but structural. Both systems show abrupt consolidation of information. To understand why these parallels matter, we look at how the brain processes ambiguous signals. Imagine listening to a faint whisper in a noisy room. Your brain receives fragmented sounds, most of which never rise into awareness. But occasionally multiple weak cues overlap, reinforce one another, and suddenly the whisper becomes understandable. This reinforcement mirrors wave interference. Weak inputs combine to produce a strong effect. Below a threshold, the effect disappears entirely. In vision, the same behavior appears in experiments using faint light flashes. When only a few photons reach retinal cells, detection becomes probabilistic. Sometimes the brain perceives the flash. Sometimes it doesn't. The transition from no perception to perception is steep. like crossing an energy barrier in a quantum system. NASA relies on similar principles when designing ultrasensitive photon detectors. The shift between noise and signal in these devices mirrors the threshold behavior seen in biological vision. Although detectors operate through physical quantum processes and the brain through biological ones, the shape of the transition is the same abrupt boundary between indeterminate and determinate states. The bridges between consciousness and quantum behavior become clearer when we examine Penrose's non-computability argument. He proposed that certain mental processes, especially insight, creativity, and sudden recognition, do not follow step-by-step computation. Instead, they appear as abrupt transitions. Problem-solving often works this way. You struggle with no progress, then suddenly the answer appears. Neural recordings show that these moments of insight coincide with synchronous bursts of gamma wave activity sweeping across the cortex, another example of threshold ignition. These bursts follow the mathematics of nonlinear dynamical systems, showing sharp regime shifts, paralleling the way wave functions collapse when probabilities reinforce one outcome over all others. Again, the connection is structural, not physical, but the echo is difficult to ignore. An even more mysterious link appears in neural quantum limited sensitivity. The brain operates close to the limits set by physics. Ion channels open in response to energy shifts on the scale of tens of millielectron volts, small enough that thermal noise and quantum tunneling begin to play roles. Some ion channels exhibit tunneling-like transitions, though governed by classical biochemical dynamics. These thresholds contribute to the all-or-nothing firing of neurons. This does not mean neurons perform quantum computation, but it shows they operate near boundaries where probability, noise, and nonlinear thresholds shape behavior, the same conditions behind quantum phenomena, even artificial neural networks. Developed by NASA for payload classification shows similar threshold effects. Small changes in input trigger abrupt classification shifts, just as weak signals in the brain trigger sudden awareness. Across domains, the same pattern returns. Systems with many interacting components produce abrupt transitions, discrete outcomes, and threshold-based behavior. As we examine blind sight, micro-awareness, neural ignition, and insight thresholds, a quiet understanding forms not that the brain is quantum, but that consciousness moves through non-linear steps that resemble quantum events. Hidden computation occurs below awareness. Signals combine and interfere. Thresholds determine what becomes conscious. Perception collapses uncertainty into a single experience. This echo between the quantum and cognitive worlds may not be coincidence. It may reveal how complex systems process information across scales. Penrose's reminder lingers. Consciousness may involve non-computable elements, not because the mind is mystical, but because it behaves in ways that resist smooth steppy step. Models with these hidden structures revealed. A final thread begins to weave through everything explored, from quantized steps to vibrating strings, from wave packets to non-locale entanglement, from superposition to threshold ignition. A thread suggesting that quantum physics, computation, and consciousness may share deeper structural principles. A thread urging us to look further toward the foundation beneath all of it. Part 10. Why do all these clues suggest we may be misunderstanding the most basic ingredient of reality itself? The deepest realization in modern science is not that particles behave strangely, or that space-time bends under gravity, or that consciousness emerges through hidden thresholds. It is the growing suspicion that matter-space and time themselves may not be the foundation of reality at all. Across quantum experiments, cosmology, and information theory, the same pattern keeps resurfacing, as if the universe is quietly insisting that reality is not built from things, but from relationships, from interactions, from networks of information that update themselves with every exchange. NASA's Quantum Foundations workshop captured this shift in a single line that now feels like the doorway to a new scientific era. Our classical picture may not describe the underlying fabric of the universe. Across a century of experiments, the clues begin to form a single thread. Follow it, and it leads to a radical possibility. The deepest ingredient of reality may not be particles or fields, but information itself. The story begins in the 1920s, when quantum mechanics first revealed that particles do not exist as solid objects with definite properties prior to measurement. Position, momentum, even identity exist only as probability distributions. The wave function, the core mathematical description of a quantum system, does not describe a thing. It describes relationships. Relationships between possible outcomes, between paths not yet taken, between interactions that have not happened when a measurement occurs. The wave function does not collapse into a physical object. Collapses into consistent information. This shift from things to information was subtle at first, hidden inside strange mathematics, but it strengthened with every decade of evidence. In the 1960s, entanglement experiments sharpened by John Bell showed that physical distance does not prevent quantum systems from behaving as one. The connection between entangled particles is not carried through space. It is encoded in shared information spanning both particles regardless of separation. Bell tests do not merely suggest this. Philosophically, they prove experimentally that the universe does not store information locally. Information is distributed. It is relational. Objects are not defined by their separation, but by their correlations. As quantum field theory matured, the picture shifted further. Fields, not particles, became fundamental. But even fields were not substances, only mathematical relationships, describing how interactions unfold. Particles became ripples in these relational fields, photons, excitations in the electromagnetic field, electrons, solutions obeying space-time symmetries, quarks, patterns inside non-abelian gauge fields. Reality ceased to be stuff. Reality became structure. Then came black holes, and with them a clue that changed everything. In the 1970s, Bekenstein and Hawking discovered that a black hole's information capacity is proportional not to its volume, but to its surface area. The event horizon, the boundary, stores the information. This implied something astonishing. The universe may function like a hologram, not metaphorically mathematically. Maldacena formalized this through a DSCFT in the 1990s, showing that a universe with gravity can be fully described by a lower dimensional theory without gravity on its boundary. Space becomes emergent, arising from informational relationships. Like pressure or temperature, it may be a derived property, not a fundamental one. Around the same time, quantum information theory emerged. Researchers showed that information is physical, not just bookkeeping, but a resource obeying thermodynamic laws. The Landauer limit tide, erasing a bit of information to a minimum energy cost. Meanwhile, quantum computing encoded information not in particles, but in state spaces. The pattern is constant. Physics describes how information changes when systems interact. Relativity offers the same hint from a different direction. General relativity describes gravity not as a force, but as geometry. Geometry is nothing but relationships between distances and durations. If matter curves spacetime and spacetime dictates motion, then the universe is not built from bricks, but from constraints, from interactions between mass, energy, and geometry. Modern physicists, from Carlo Rovelli to Mark van Romsdonk, interpret these relationships as informational structures. Spacetime curves because the underlying information network bends. Quantum gravity models, from loop quantum gravity to tensor networks and spin foams, suggest that spacetime is not continuous, but built from discrete informational connections that only appear smooth at large scales. Even cosmology echoes the same theme. Data from WMAP and Planck shows that faint ripples in the cosmic microwave background emerge from quantum fluctuations in the early universe. These patterns did not come from matter acting like pixels. They arose from correlations in quantum fields, stretched across space by inflation. The cosmic web is shaped not by particles pushing one another, but by the evulsion of information encoded in those correlations. Across every scale, from black holes to galaxies, from qubits to space-time itself, the universe behaves less like a machine made of objects, and more like a self-updating web of information. Reality may not be made of things. It may be made of relationships. Galaxies form along vast cosmic filament structures, born from the collapse of density fluctuations encoded in the earliest information of the cosmic microwave background. When the James Webb Space Telescope peers more than 13 billion years into the past, it finds galaxies forming sooner and more intensely than many classical models predicted. Early hints that our assumptions about structure formation may not fully capture how information flowed through the infant universe. Across every scale, from quantum events to the cosmic web, the same pattern appears. Matter is not fundamental. The relationships that matter follows are dart to see how deep this idea goes. Reconsider entanglement, but through the lens of Spaini. In 2010, physicist Mark van Romsdonk proposed a striking idea. Spacetime itself may be woven from patterns of quantum entanglement. Reduce entanglement, and spacetime stretches. Remove it entirely, and spacetime tears apart. This concept found support in tensor network simulations, showing that increasing connectivity between qubits produces structures resembling curved space. In this view, distance, curvature, and the shape of the universe emerge from the density of informational links. NASA researchers working on quantum communication systems often describe entanglement as a resource enabling correlations beyond classical limits. Operational language, yes, but beneath it lies something profound. Entanglement describes relationships, not objects, and those relationships appear to shape the geometry of the universe. If information is fundamental, many quantum puzzles suddenly clarify. The wave function encodes available information, not hidden properties. Collapse selects a consistent informational outcome, Entanglement expresses correlations that transcend distance. Black hole thermodynamics links information to boundary area. Space-time curvature arises from informational structure. Pieces, once scattered, now begin to align. What if the universe is not built from particles? What if particles are emergent events, stable informational patterns arising from deeper networks? What if space is not a container? What if it is a map of how information is connected? What if time is not a flow? What if it is the ordering of informational updates? What if reality is a computation not digital, but defined by operations, interactions, and correlations? These questions do not emerge from philosophy. They emerge from data. And as the clues accumulate, the horizon stops looking like a boundary and starts looking like a threshold. Every concept we encounter, quantized energy, vibrating strings, wave packets, entanglement, superposition, neural thresholds, points toward the same quiet suggestion. We may be standing between two ways of understanding the universe. One built from things, one built from information, and perhaps in centuries to come, physics will evolve from describing particles and fields to describing relationships and informational flows. The true fabric beneath the world we see. Thank you for traveling through this exploration, for letting curiosity rest beside understanding, and for giving science a quiet place to unfold. If this journey offered even a moment of clarity, wonder, or calm, I'm grateful you chose to share it. A gentle tap on subscribe or like isn't just support, it's encouragement that helps me continue shaping these night voyages. And if you'd like to share where you're listening from or any thoughts this sparked, I would be honored to hear. May your night be peaceful, and may the universe settle softly around you as you drift into rest.